What if I told you that the very sun we depend on for life could one day transform into an all-consuming beast? Imagine this. A seemingly normal day on Earth suddenly plunges into chaos as the sun expands into a monstrous fiery titan. Visualize the skies morphing from serene blue to a hellish red as our planet is inexorably pulled into this cosmic inferno. With the sun's intense heat vaporizing our oceans and turning our atmosphere into a blistering furnace, humanity could face extinction on a scale so grand, it's almost unimaginable. This isn't a scene from science fiction, it's a terrifying reality that might await us. In this spine-chilling exploration, we'll uncover the shocking truth about how the sun's catastrophic expansion could herald the end of our world. Brace yourself as we navigate the harrowing stages of our planet's fiery demise. Stay with us, because what you're about to witness is the ultimate end of everything you know, the birth of a star. Our journey begins approximately 4.6 billion years ago, in the vast and ancient expanse of space, within a colossal molecular cloud, often referred to as a stellar nursery, situated in the Orion arm of the Milky Way galaxy. This cloud, a vast expanse of hydrogen molecules interspersed with traces of helium and heavier elements, spans light years in diameter. Within this cloud, regions of higher density began to form due to gravitational instability, possibly triggered by the shock waves from nearby supernovae. These regions, known as clumps, grew denser over time as they collapsed under their own gravity. As these clumps contracted, their temperature and pressure increased, leading to the formation of a rotating disk of gas and dust around a central core. The core's continued contraction led to temperatures soaring to millions of degrees Celsius. This heat resulted from the conversion of gravitational potential energy into thermal energy. Once the core reached temperatures sufficient to overcome the electrostatic repulsion between hydrogen nuclei, nuclear fusion reactions. These reactions, where hydrogen atoms fused into helium, released an immense amount of energy in the form of light and heat, marking the birth of a protostar. Simultaneously, the surrounding protoplanetary disk began to cool and condense. Over millions of years, particles within this disk collided and coalesced to form planetesimals and protoplanets, laying the foundation for our solar system. The newly formed star, now a protostar, experienced vigorous solar winds that expelled excess gas and dust from the system. This process led to the establishment of a stable main sequence star, the Sun. This foundational phase not only marked the Sun's birth, but also set in motion the formation of the planets, moons, and other celestial objects within our solar. Understanding this formation process is crucial as it provides the basis for the Sun's subsequent evolution and its eventual impact on Earth. The Sun's stable phase. The Sun has been in its stable phase, known as the main sequence, for approximately 4.6 billion years and will remain in this state for about another 5 billion years. During this time, the Sun has maintained a steady output through the process of nuclear fusion occurring in its core. In this stable phase, hydrogen nuclei, protons, fuse into helium through a series of reactions known as the proton-proton chain. These reactions occur under extreme conditions in the core, where temperatures reach around 15 million degrees Celsius, and pressures are about 250 billion times that of Earth's surface. The energy produced from these nuclear reactions is transported outward through the Sun's internal layers. In the radiative zone, which extends from the core to approximately 70 of the Sun's radius, energy is transported by radiation. Photons, or light particles, travel through this layer at a slow pace, taking hundreds of thousands of years to reach the convective zone. In the convective zone, which comprises the outer 30 of the Sun's radius, energy is transported by convection currents. Hot plasma rises towards the surface, cools, and then sinks back down, creating a dynamic pattern of convective cells that contribute to solar activity. The photosphere, the visible surface of the Sun, is where the majority of solar radiation is emitted. With a temperature of about 5,500 degrees Celsius, the photosphere's light provides the warmth and illumination essential for life on Earth. The Sun's energy output, or luminosity, remains relatively constant during this phase, sustaining the conditions necessary for life. This stability is a result of a delicate balance between the inward pull of gravity and the outward pressure from the sun's consistent energy output and predictable behavior have played a fundamental role in shaping Earth's climate and supporting diverse ecosystems. Understanding this phase is crucial for comprehending the conditions that have allowed life to the red giant phase. As the sun ages and exhausts its core hydrogen supply, it will undergo a dramatic transformation into a red giant. This transition, predicted to commence in approximately 5 billion years, will mark a significant departure from the sun's stable main sequence phase. Once the hydrogen in the core is depleted, the core will contract under the influence of gravity, increasing both its temperature and pressure. This contraction will trigger the ignition of helium fusion in the core, where helium nuclei will fuse to form carbon and oxygen. The onset of helium fusion will produce additional energy, causing the sun's outer layers to expand massively. During the red giant phase, the sun's diameter will increase to roughly 100 times its current size, potentially engulfing the orbits of Mercury, Venus, and possibly Earth. The outer layers of the sun will cool and emit a reddish hue, giving the red giant its name. The increase in size will lead to a significant rise in the sun's luminosity, making it thousands of times brighter than it is today. This heightened luminosity will result in intense solar radiation, drastically altering the solar system's climate. In addition to the expansion, the sun will experience powerful solar winds that will blow away its outer layers, forming a planetary nebula, a shell of ionized gas and plasma surrounding the remaining core. This phase represents a critical juncture in stellar evolution, with profound implications for the solar system. The transformation into a red giant will reshape the environment of any remaining planets and could lead to the destruction of those within the sun's expanded reach. Understanding this phase is essential for predicting the future conditions of our solar system and the chapter number 4, the sun's expansion and Earth's fate. As the sun evolves into a red giant, its expanding size and increased luminosity will have profound effects on Earth. The initial impact will be a dramatic rise in global temperatures, leading to the melting of polar ice caps and glaciers. This melting will result in rising sea levels, causing widespread flooding of coastal regions and altering ocean currents. As the sun's energy output continues to rise, temperatures on Earth will climb sharply, triggering a runaway greenhouse. The runaway greenhouse effect will cause extreme global warming, with surface temperatures reaching levels that will render Earth uninhabitable. The atmosphere will become increasingly thick with water vapor and other greenhouse gases, further trapping heat and accelerating the warming process. Eventually, the intense heat will break down atmospheric molecular bonds, leading to the loss of the atmosphere and exposing Earth to the harsh conditions of space. As Earth approaches the sun, the planet's surface will experience severe thermal stresses, causing the disintegration of rocks and soil. The biosphere will be severely disrupted, leading to the extinction of all known life forms. This process will unfold over millions of years, but the rapid changes will ensure that Earth's environment becomes increasingly hostile long before the planet is ultimately engulfed by the expanding sun. This chapter provides a detailed account of the potential consequences for Earth and offers a sobering glimpse into the future of our planet as it faces the ultimate cosmic transformation. The timeline of Earth's engulfment. To vividly illustrate the stages of Earth's engulfment by the expanding sun, we present a hypothetical accelerated timeline that compresses billions of years into a condensed period. Initially, as the sun begins to expand, we will observe rapid increases in solar radiation and temperatures on Earth. The melting of polar ice and flooding of coastal regions will occur within a few 100,000 years, leading to significant changes in the planet's surface and climate. As the sun continues its expansion, we'll witness the evaporation of the oceans and the intensification of the greenhouse effect. Temperatures will rise dramatically, causing the atmosphere to thicken with water vapor and other greenhouse gases. This process will accelerate global warming, leading to extreme conditions that will make Earth uninhabitable within a few million years. Eventually, as Earth gets closer to the sun, the gravitational forces will stretch and distort the planet. Intense heat and solar winds will strip away the atmosphere, leaving Earth exposed to the vacuum of space. The surface of the planet will undergo complete vaporization, resulting in a barren, lifeless rock. This accelerated timeline offers a dramatic visualization of Earth's final moments and highlights the scale and intensity of the changes that will occur as the Sun engulfs our planet. Chapter number 6. Detailed analysis of the Sun's future. Following the red giant phase, the Sun will shed its outer layers, forming a planetary nebula and leaving behind a dense, hot core known as a white dwarf. This transition involves complex nuclear reactions and significant mass loss through powerful solar winds. The white dwarf will be approximately the size of Earth, but with a mass comparable to that of the Sun. Initially, it will be incredibly hot, with temperatures exceeding 100,000 degrees Celsius, but over billions of years, it will gradually cool and fade. The remnants of the planetary nebula will disperse into space, contributing to the enrichment of the interstellar medium with elements like carbon and oxygen. These elements will eventually become part of new star systems and planetary systems, continuing the cycle of cosmic evolution. The fate of the Sun as a white dwarf will mark the end of its stellar life cycle, but its influence on the cosmos will persist through the legacy of the elements it has contributed to the universe. This chapter offers a detailed analysis of the scientific processes involved in the Sun's final stages, providing a comprehensive understanding of the physical and chemical changes that will occur as the Sun transitions from a red giant to a white dwarf. It also explores the broader implications of these changes for the future of the solar system. What happens if the Sun swallowed Earth? As the Sun expands into a red giant, it will alter the gravitational dynamics of the solar system, potentially leading to the engulfment of Earth. The immense increase in the Sun's radius will likely bring Earth into contact with its outer layers. This process will be accompanied by intense heating and tidal forces that will stretch and distort the planet. The gravitational forces exerted by the expanding Sun will create significant tidal effects on Earth. These tidal forces will cause seismic activity, including massive earthquakes and volcanic eruptions. As the planet approaches the Sun's outer layers, the atmosphere will be stripped away by solar winds, and the surface will undergo extreme thermal stresses. The increased solar radiation will cause the planet's surface to vaporize, leading to the complete disintegration of Earth. Understanding the consequences of Earth's engulfment by the Sun provides valuable insights into the future of our planet and the potential for cosmic events to reshape our solar system. This chapter examines the various processes involved in the engulfment scenario and explores the broader implications for the solar system and beyond, hypothetical scenarios and preparations. As we face the inevitable future of the Sun's transformation into a red giant, humanity must grapple with the colossal challenge of ensuring our species' survival. In this chapter, we delve into the hypothetical scenarios and advanced preparations that could help us navigate this cosmic upheaval. With the Sun's expansion poised to engulf Earth, exploring potential solutions and technological innovations becomes paramount. Our journey begins with the concept of space colonization, a visionary approach to safeguarding human life. Space colonization involves the establishment of human habitats beyond Earth, potentially on other planets or moons within our solar system. One of the primary candidates for such colonization is Mars. Scientists have long proposed the terraforming of Mars, altering its atmosphere and surface to make it more Earth-like. This ambitious project would involve increasing the planet's temperature, creating a stable atmosphere, and possibly introducing water sources. While this idea is fraught with scientific and engineering challenges, advances in technology could make it feasible in the distant future. We will examine the technological hurdles of such an endeavor, including the need for advanced life support systems, sustainable energy sources, and the development of habitat structures capable of withstanding Martian conditions. Another intriguing option is the construction of massive space habitats or orbital colonies, which could serve as self-sustaining environments for human life. These habitats would need to provide all the essentials for human survival, such as oxygen, food, and water, while also shielding inhabitants from the harsh conditions of space. We will explore various design concepts for these habitats, including rotating space stations to simulate gravity and advanced recycling systems to manage resources. In addition to Mars, moons like Europa and Titan are also considered potential candidates for human habitation. Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust, which might harbor the necessary ingredients for life. Titan, Saturn's largest moon, has a dense atmosphere and liquid lakes of methane and ethane, presenting unique opportunities for scientific exploration and potential colonization. We will discuss the challenges associated with establishing habitats on these moons, including the extreme temperatures, lack of breathable atmosphere, and the need for advanced technology to access and utilize local resources. Expert interviews will provide insights into the feasibility of these scenarios, highlighting the latest advancements in space technology and the research needed to turn these dreams into reality. Scientists, engineers, and futurists will share their perspectives on the innovations required to make space colonization viable and the potential impact on humanity's future. This chapter serves as a testament to human resilience and ingenuity in the face of cosmic challenges. By considering these hypothetical scenarios, we gain a broader perspective on our place in the universe and the steps we might take to ensure our long-term survival. Reflecting on these possibilities emphasizes the importance of forward thinking and preparation as we advance our understanding of space and our capabilities to thrive beyond Earth. Conclusion: as we draw this extensive exploration to a close, we reflect on the profound journey we've undertaken from the sun's genesis to its eventual fate and the future of humanity. This documentary has traversed billions of years of cosmic evolution, unveiling the intricate processes that define the life cycle of stars and their impact on their planetary systems. We began by witnessing the birth of our sun from a primordial molecular cloud, observing its transition from a protostar to a main sequence star. We explored the stable phase of the sun, where nuclear fusion powered its steady glow and provided the conditions necessary for life on Earth. The narrative then led us to the red giant phase, revealing the dramatic transformations the sun will undergo as it exhausts its hydrogen fuel, and the potential impact of the sun's expansion on Earth was thoroughly examined, highlighting the catastrophic consequences of extreme global warming and atmospheric loss. This stark vision of our planet's future underscores the fragility of life in the face of cosmic forces. We delved into the sun's ultimate transformation into a white dwarf and its eventual cooling into a black dwarf, marking the end of its active life. In contemplating the future, we explored hypothetical scenarios and preparations that could offer solutions for humanity's survival. The concept of space colonization and the technological challenges of establishing habitats on Mars, moons like Europa and Titan, and building orbital colonies were examined in depth. These discussions illuminated the resilience and creativity required to navigate the cosmic challenges that lie ahead. Our journey through time and space has provided valuable insights into the dynamic nature of the universe and our place within it. Understanding the sun's life cycle and the potential for future exploration and adaptation enriches our appreciation for the cosmos and the ongoing quest for knowledge. As we continue to explore and innovate, we are reminded of the importance of preparing for the future, embracing change, and seeking new frontiers. Thank you for joining us on this epic journey through the evolution of our sun and the fate of our planet. Stay curious.